Hi guys, welcome to the next lesson on dilution of acids and bases. In this lesson, we're going to be looking at diluting acids and bases in solutions and being able to calculate. As we've already talked about, the concentration of acids and bases is usually expressed in moles per litre, or capital M. And the dilution of these can occur as follows. We're familiarising you with some terms. Here we have hydrochloric acid. It has 10 ml of volume, and it is 10 moles per litre, which is known as 10 capital M. We've taken then 10 mils of that volume, 10 mils of it here, it's been taken out by what's known as a pipette, which is this instrument here. We've then placed that 10 mils of the hydrochloric acid into what's known as a volumetric flask. So this volumetric flask over here contains now an amount of water, and we've added 10 mils of it to the volumetric flask. We've then added water to that volumetric flask, and we can see that we have made up a final volume over here of what's known as hydrochloric acid and water. Because the hydrochloric acid has had water added to it, it must be diluted, or it must have a smaller concentration than what we began with. Because the volume of the solution has changed, it's increased, therefore the concentration must have decreased. There'll be now less moles per litre of hydrochloric acid in this one than there was in this one. But the moles of the two solutions have not changed. Because the moles of the solutions have not changed, we can apply this formula to calculate the dilution of the solution, where C1, the initial concentration, is multiplied by V1, the initial volume, and that's equal to C2, which is the final concentration, multiplied by the final volume, V2. Let's look at a problem with this. Calculate the molar concentration of hydrochloric acid when 10 mils of water is added to 5 mils of 1.2 molar hydrochloric acid. So again, applying this formula, we can see that we've had 10 mils of water added to 5 mils of hydrochloric acid. Therefore, our final volume must be 15 mils, which is what's written here. We have a final volume of 15 mils. The initial concentration was 1.2 molar. The initial volume was 5 mils. The final volume is 15. We need to find, or we want to find, the molar concentration of the final solution. So in order for that to happen, we need to know C2. In order to calculate C2, we rearrange the equation where we divide this side by V2 to get C2 by itself, which means we'll have C2 equals C1 times V1 over V2. Notice here that the volumes of the two solutions are in milliliters. It's okay to express or write your answers in milliliters when you're completing the equation. However, all of your units need to be milliliters if that's the case. You cannot have 0.005 litres and 15 mils. They both need to be in milliliters. So all measurements in milliliters or all measurements in litres. Divide 5 by 15, multiply that by 1.2, and that gives me 0.4 molar. So my initial concentration was 1.2, and my final concentration is now 0.4. So I've had a reduction in concentration, which makes sense because I've added water, I've increased my volume, so I'll therefore have a less concentration. This next problem, it's asked us to calculate what pH of the diluted solution would be, where we have 5 mils of nitric acid, 0.01 molar nitric acid, and it's diluted to 100 mils. What will the final pH be? So first of all, let's write an equation. That nitric acid behaves as a strong acid. When we add it to water, it will form by a complete reaction, or a forward reaction arrow, H3O plus, and the nitrate ion. So we can see that every single one of the original nitrate ions, 0.01 molar, will become the concentration of the final hydronium ions, 0.01 molar. Keep that in mind in a little bit. So the initial concentration is 0.01, the initial volume is 5 mils, and the final volume is 100 mils. We need to calculate the final concentration because we want to work out the amount of the diluted solution. The amount of the diluted solution will be the concentration of hydronium or the concentration of nitric acid, and then we can use that to help us calculate the pH of the solution by subbing in the concentration of H3O. So first of all, we calculate the concentration of C2, just as we did in the previous slide. We multiply the initial concentration by the initial volume, and we divide that by the final volume, and that gives us this molar concentration of nitric acid. So we can see that nitric acid has a concentration now of 0.0005 molar. As I mentioned, because this is a complete or forward reaction, every single one of the nitric acid molecules will form a hydronium molecule or hydronium ion. Therefore, the concentration of the two will be equal. So we can place this number into the pH formula, negative log 10, 0.0005, which gives you a pH of 3.3. We can validate or check our answer is correct by placing the pH formula of 0.01. So the initial pH, 0.01, into the negative log 10 formula gives you a pH of 2. We have gone from a pH of 2 to a pH of 3, which means we've increased the pH. The pH has gone higher, which means we must have an increase in pH, as you can see here, but we have a decrease in the concentration of hydronium ions. So we can see that our answer is true, or it is correct. The second example is shown over here. We've got 10 mils of sodium hydroxide, and that's diluted 100 mils. We need to calculate the pH of the final solution. Again, pH is calculated by negative log 10, concentration of H3O, multiplied by the concentration of H3O. Before we can calculate the concentration of H3O, we first need to calculate the concentration of OH. Because if we have a solution of sodium hydroxide is added to water, and in doing so, it's a strong base, so we're going to form sodium ions, we're going to form hydroxide ions, and we'll also have water here. So sodium hydroxide breaks up, and we have the same concentration over here of sodium hydroxide as we do hydroxide ions. But when we dilute the solution, we started with 0.1 molar sodium hydroxide, we finished with 100 mils, and we began with 10 mils. What's our final concentration? We use the same formula to help us calculate this. We have 0.1 times 10, again in mils, and again in mils here for 100. And we have 0.01 molar as our final concentration. This refers to the concentration of hydroxide, because as I mentioned, every single one of these sodium hydroxide molecules will break up and form sodium ions and hydroxide ions. Therefore, we've calculated the concentration of hydroxide ions over here after it's been diluted, which is 0.01 molar. We now need to use the Kw formula to help us work out the concentration of hydronium before we can then work out the pH. So the concentration of hydronium is equal to 1 times 10 to the negative 14 divided by 0.01, which gives you 1 times 10 to the negative 12 molar of H3O. So that tells us that there's a very small amount of H3O, which makes sense because we're dealing with a basic solution. We then place the amount of hydronium ions into the pH negative log 10 formula, which gives us a pH of 12. So we have a high pH, which suggests that we have little amounts or low amounts of H3O, and we have lots of OH ions, which again validates our answer. Lots of OH ions, not many H3O ions, therefore a high pH. So now we should understand dilution of acids and bases can be done with this formula, and to calculate the pH of a diluted solution or a strong diluted acidic solution, we must be having a gain in pH. The pH must be getting higher. So you start with a pH of 2 perhaps, you end with a pH of 3 or higher because it's diluted. To calculate the pH of a diluted strong basic solution, we must be getting a lower pH because we're starting with a high pH, say a 10, we move to an 8. You should now be able to calculate the concentration using this formula and describe and calculate pH and pO